Hello guys, Tebang Padi here. On this video, we'll be doing introduction to PIC microcontrollers assembly language, looking specifically at the PIC16F84A. Okay, let's get started. At the end of the video, I'm expecting you guys to be able to explain what a microcontroller is, the basic microcontroller system, basic microcontroller capabilities, what are the building blocks of your microcontroller, functions of those building blocks, and how to connect digital inputs and outputs to your microcontroller. Now we look at the PIC16F84A, looking at its hardware, and then the functions of those hardware pins. We look at the memory organization and special function registers. And then we look at the basic assembly instructions and programming. Now, what is a microcontroller? A microcontroller can be seen as a small computer on a single integrated circuit because it contains in that integrated circuit the processor, memory, programmable I/O pins, and other peripherals, which includes ADC, serial ports, timers, and other form of communication can be either serial or USB depending on the microcontroller. So all of these are in the single integrated circuit. Hence we say it can be seen as a small computer on a single integrated circuit. But of course it has limitations compared to what a computer can do. The basic microcontroller system is where you have an input, control, and output. Basic microcontroller system. The input can be either switches, sensors, or some sort of communication to the microcontroller. The microcontroller will process and compute the information and then give you the results or the output as either visual, audio, some sort of communication, or switching on and off whatever is connected to the I/Os of the microcontroller. Right. Now, what are the capabilities of a microcontroller? Microcontroller is programmable. That's one thing, very important. It has configurable hardware functionality. Here we mean that the pins, certain pins, can be configured as either inputs or outputs. They are not fixed inputs, they are not fixed outputs. They can be configured to be either inputs or outputs. It can perform specific or multiple tasks depending on the program that has been written and programmed into the microcontroller. It has other peripherals built in it. It has timers built in it. It has ADCs built in it. It has serial communication built in it, and other forms of communication like the I2C or SPI as part of the control. Now, what are the building blocks of the microcontroller? Microcontroller, it has the CPU for fetching and executing instructions and also for performing arithmetic. It has program memory for storing the program during the programming process. Data memory for storing user data. And then the data can be stored in a volatile RAM or non-volatile EEPROM memory. And now you have input, output pins, I/O pins for interfacing the rest of the circuit to your microcontroller, for connecting your sensors to your microcontroller, for connecting your LEDs to your microcontroller. You do that through the input-output pins, right? It has built-in timers, which can be used as counters or to implement delays, or even to implement a real-time clock, right? And it has other peripherals like ADCs, serial communication, which you may use if there's a need for that in your application. These are the basic building blocks of your microcontroller. And now, how do you connect inputs and outputs to your microcontroller? We're looking at the digital inputs and outputs here. Now, the first thing to note is that Your PIC microcontroller can sink or source a maximum of 25 milliamps per pin. Each and every pin can sink or source a maximum of 25 milliamps. A sink means when the current is flowing into the microcontroller, into the pin of the microcontroller, that current should not exceed 25 milliamps. Source means if the current is flowing out from the pin of the microcontroller, that current should not exceed 25 milliamps. Connecting inputs to your microcontroller, we can use the pull down configuration, where the input of the PIC is connected to ground through a pull down resistor. The reason is the pin can never be left floating. We cannot erase this resistor and the ground and just have a switch connecting to the input, because when that pin floats, the input state of that pin will not be reliable. At some point it will jump between high and low, giving an unreliable state. We have to pull it down through the pull down resistor, and then when the switch is open, the logic input is 0. The logic input is 0 when the switch is open, and when you close the switch, the current flows through into the input of the microcontroller. Yes, some current will also flow through the pull down resistor, but surely the current will flow into the input of the microcontroller, giving it logic 1. Right. Second configuration, pull up configuration. In this case, the pin of the microcontroller is connected to VCC, to logic 1, through a pull up resistor. Right. So when the switch is open, current is flowing into the microcontroller through that pull up resistor. When you close the switch, because there will be 0 resistance between the input and the ground, the current will flow directly to the ground and no current will be flowing into the input of the microcontroller, giving logic 0 there when the switch is closed. Right. Basically, these are the 2 configurations you can do to connect your digital inputs to your microcontroller. Of course, when connecting sensors can provide logic 1 and 0 directly, so you won't need the pull ups and pull downs. Some sensors you can connect them directly to your input output pin. Right. Connecting outputs to your microcontroller, there's 2 ways as well. Where in the first case, it is the sinking, where the current is flowing from the supply through the resistor and the LED into the I/O of the microcontroller. We say it is sinking, and then we said that current must not exceed 25 milliamps. The other configuration is when the current is flowing out of the PIC microcontroller's I/O pin through the resistor and the LED to ground, and we say it is sourcing. Now, this current should also not exceed 25 milliamps. Right. And now, let's look at the PIC16F84A. Basically, depending on which microcontroller you are interested in and you are willing to use in your application, it is important that you know the hardware of that microcontroller so that you can construct your circuit correctly and you can assign your inputs and output pins where you have to, or where it is possible for you to do so. Right. Now, looking at the PIC16F84A, we have what we call port A pins. Port A pins are port RA is pin RA0, RA1, RA2, RA3, and RA4 pins. In total, we have 5 pins on port A, and we have port B pins starting from B0, B1, B2, B3, 4, 5, 6, 7. We have 8 port B pins. Both port A and port B pins are programmable input-output pins. Port A and port B pins are programmable input-output pins, meaning you can choose either of those pins to be either your inputs or your outputs. Right. And then we have the M clear pin, pin 4, M clear. This is a reset pin. This pin should be always at logic 1 for normal operation, for the PIC to execute the program installed in it. But when the logic on this pin goes to 0, when this pin is connected to ground somehow, the PIC will stop executing instructions. It will stop executing instructions, and it will only start again from the beginning when that pin is released back to logic 1. Hence, mclear, or sometimes known as a reset. Mclear reset. Right. Pin 5 is VSS, it's your ground. I've talked about B0 to B7. Pin 14 is your VDD, it's your supply pin. Meaning pin 5 and 14 are for supply, where 5 is for ground, and then 14 is for your positive supply. The PIC can start operating from 2 volts to a maximum of 5.5 volts. So you put in 2 volts to a maximum of 5.5 volts, it will start executing instructions and perform as it is expected. Right. Pin 15 and 16 for this microcontroller, they are for oscillator input. There are different oscillator configurations, but pin 15 and 16 are for the oscillator input. Right. And on the next slide, that's what I'm explaining. VDD, it's for supply. Normally, we supply the microcontroller with 5 volts, but it works from 2 volts to 5.5 volts. VSS is your ground, it's pin 5. mclear, it's your reset. When the pin is low, the PIC goes into reset. Right. And then pins 15 and 16 are for your oscillator. Port A is pin 1 to pin 3, pin 17 and 18. These are programmable input output pins on port A. And then port B is pin 6 up to pin 13. These are programmable input out pins on port B. Right. Now, programming the PIC microcontroller. What do you need to know before you can start programming your PIC microcontroller in assembly language? You first need to know your microcontroller hardware. In this case, we have looked at the PIC16F84A hardware. You need to know your hardware, where your pins, your inputs, output pins are, and what are the capabilities of those input output pins. You need to know that. And now you also need to know the memory organization of your microcontroller, and more especially what we call special function registers, because these registers are the ones that helps you control your microcontroller. And then the third thing that you need to know is your assembly instructions. Once you know your microcontroller hardware, you know the memory organization and special function registers, and you know your assembly instructions, then you can use your assembly instructions together with your special function registers to configure and control your microcontroller hardware. You use your assembly instructions together with the special function registers to configure and control your microcontroller hardware. You first need to know your microcontroller hardware, you need to know your special function registers, and then you need to know your assembly instructions. Then you use the assembly instructions together with the special function registers to control your microcontroller hardware. Right. Now let's get started. Looking at the memory organization and then the special function registers. We have already looked at the hardware. Now we are looking at the memory organization and then the special function registers. Now the PIC16F84A has 2 memory blocks, being the program memory and the data memory. Now the data memory is divided into special function registers, the ones here on top with names, and then the general purpose registers, the 64 general purpose registers. Now this data memory is also divided into banks, being bank 0, the first block, and then bank 1, the second block. Right. Now the general purpose registers are used to store user data, and then the special function registers controls and monitors the specific or various aspects of your microcontroller. Right. The special function registers, they either monitor or control certain aspects of your microcontroller. Right. We'll look at what those aspects are and which special function registers controls or monitors what part of your microcontroller. The most important thing to note here is that your data memory is divided into two blocks, being bank 0 and bank 1. If you want to access a register in bank 0, you must be in bank 0. If you want to access a register in bank 1, you must be in bank 1. There's no way you would want to write to a register in bank 1, yet you are in bank 0. You are going to write to the wrong register. We'll also look at how you switch between the two banks. Right. Now, examples of special function registers. We said special function registers, they control or monitor specific aspect of your microcontroller. Now, let's look, for example, at the trace register. The trace register, we have trace A and trace B register. Both they are in bank 1. Trace A and trace B registers as the special function registers. What are their roles in this microcontroller? The trace A register found in bank 1, its purpose is to configure your pins as either inputs or outputs. Specifically, trace A for port A pins. So trace A is used to set up your pins as either inputs or outputs, but your pins which are on port A, right? Trace B register, also in bank 1, it is used to configure your I/O pins on port B, right? Now the port registers found in bank 0, we have port A and port B. The port registers are for reading or writing to the I/O pins, right? Port A, you use it to read or write port A pins, and then port B, you use it to read or write to port B pins, right? You read or write to the pins depending on whether they are configured as inputs or they are configured as outputs. So if a pin is an input, you are going to read it using the port register. If a pin is configured as an output, you are going to write to it using the same port register, right? Now, the trace registers are for configuring the pins as either inputs or outputs. The port registers are for reading or writing to the pins, right? Now, how do we switch between the two banks? Bit 5 of the status register is used to switch between the banks. Now, the status register is found in both banks. In bank 0, you have status register. In bank 1, you still have status register. Now, bit 5 of the status register is used to switch between the banks. When you set that bit, you are switching to bank 1, meaning when bit 5 is set, it means we're in bank 1. When bit 5 of the status register is cleared, it means we're in bank 0. That's how you switch between the banks. You want to jump to bank 1, you have to first set bit 5 of the status register. That will take you into bank 1. You want to go to bank 0, you have to clear bit 5 of the status register. That will take you to bank 0. Right. Now, basic registers and instructions. All the registers we have been referring to. Port A, port B, trace A, trace B, the status register. All of the registers found in here, even the general purpose registers, they are all 8-bit registers. They are all 8-bit registers, and then they are non-volatile. They are actually volatile, meaning when you remove power, the data on those registers is lost. They are actually volatile, not the other way around. And then, since all registers are 8-bit registers, in some registers, some bits will be useful, some bits will be useless or unused, to say. Now, all registers are 8-bit registers. We have bit 0 up to bit 7. On the right hand side, the least significant bit. On the left hand side, the most significant bit. And now we have instructions that can affect a single bit in the 8-bit register. Now those instructions are called bit-oriented instructions. They modify or affect only one bit in the whole 8-bit register. And now these bits, like I said, they affect a single bit in a register, And then examples are the bit set file. So let's say, for example, we say bit set file port A bit 4. Your file or your register is port A, and then the bit you want to set is bit 4. Let's assume that this is your port A register, and then bit 4 will be set according to the instruction. Bit set file set bit 4 of the port A register. That bit will be made 1. The rest of the other bits will remain unchanged. If it was 1, it's going to remain 1. If it was 0, it's going to remain 0. Only this one will be set. If it was set, it's going to remain set. But if it was 0, it's going to change to being set, being 1. Right. So these are called bit-oriented instructions. They affect only one bit of the 8-bit register. Then we have byte-oriented instructions and literal instructions. Now, these instructions, they affect the whole 8 bits of a register. Byte-oriented instructions and literal instructions, they actually affect the whole 8 bits of a register. Right? Examples, in this case, let's say we use the move a literal value into W. W being our register, normally said to be the working register. Move a value into the working register. The value that we want to move into the working register is 3F in hexadecimal. Hexadecimal value 3F. We move it into W. And now this is our W register. The first nibble, it's 3. The second nibble, it's F, 3F. So that's actually supposed to be 1, not a 0. So it's supposed to be 3F. Right. We move 3F into W. That's what will be in W. Right. And then we have what we call branching instructions or control instructions. These instructions jumps from one location of the program to another, and then sometimes you can return back to the original location, and sometimes you don't even have to return. Now, example of those instructions are go to instructions, the call instructions, and then the return instructions. To get a clear picture of all the possible or the basic instructions for the PIC16F84A, please download the PIC16F84A datasheet and then look under instruction set for explanation on all the instructions and what they can do. Right. Now, how do we configure the pins? How do we configure the I/O pins of your microcontroller? Like I said, the trace registers are used for configuring the pins as either inputs or outputs. Now, the trace registers are the special function registers, and then the purpose of the trace register is to configure your pins as either inputs or outputs. Now, trace A is for configuring port A pins, and then trace B is for configuring port B pins. Port A pins, we have A0 to A4. For port B pins, we have B0 to B7, meaning we have 8 pins on port B, we have 5 pins on port A. Right. When a trace bit is set, either trace A or B, when any trace bit is set, meaning the logic level of that bit is made 1, logic 1, the corresponding port pin is configured as an input. If you want to make a pin an input, you must set the corresponding trace bit of that pin. Right. Now, when a trace bit is cleared, the corresponding port pin is configured as an output. To make a pin an output, you must clear its corresponding trace bit. Right. An example, make A0, A3, and A4 inputs, A1 and A2 outputs on port A. We want you to make A0, A3, and A4 inputs, and then A1 and A2 outputs on port A. Then what value must you move into trace A to configure A0, A3, and A4 as inputs? A0 must be set, because when the trace bit is set, the corresponding pin is an input. A0 must be set on trace A, A0 must be set, and then A3 must be set, and then A4 must be set. And then remember, on port A or on trace A, we don't have A5, A6, A7. And for that reason, they will all be 0. A5, A6, A7, they will always be 0 because we don't have input-output pins corresponding to A5, A6, A7. Right. Now, we want to make A1 and A2 outputs, A1 and A2 outputs. To make a pin and output, the corresponding trace bit must be 0. So A1 must be 0, A2 must be 0. Right. And now, what is the overall 8-bit value? Higher nibble, that is 1 in hexadecimal. The lower nibble, that is 9 in hexadecimal. So we move 1 9 into trace A. We will have configured our pins A0, A3, and A4 as inputs, A1 and A2 as outputs. Right. Now on trace B, or on port B, make B0 to B3 inputs, make B4 to B7 outputs. On port B, make B0 to B3 inputs, make B4 to B7 outputs. To do that, for inputs, the corresponding trace bits must be logic 1, must be set. A trace bit is set, it means the pin is an input. A trace bit is cleared, it means the pin is an output. So to make B0 to B3 inputs, we must set B0, B1, B2, and B3 for trace B. B0, B1, B2, and B3 are set to make B0 to B3 inputs. B4 to B7, they must be outputs. So B4, B5, B6, B7, those trace bits must be 0 to make the pins outputs. Right. So we move value in hexadecimal 0F into trace B to make those pins B0 to B3 inputs, B4 to B7 outputs. Now, on trace A and on port A, although we don't have A5, A6, A7, those registers are still 8-bit registers. So, the A5, A6, A7, we can make them zeros all the time because they are unused. But they are still there because the register, it is still an 8-bit register. Now, how do we switch between the banks? We talked about using bit 5 of the status register to switch between the banks. Right. Now, to do that, when we set bit 5 of the status register, that means we go into bank 1. When bit 5 of the status register is set, it means we are going to bank 1. And then that means we can access, read or write to the registers in bank 1 after switching to bank 1. We first switch to bank 1, then we can access registers in bank 1, be able to read and write to those registers. Now, to go to bank 0, we need to clear bit 5 of the status register. We need to make bit 5 of the status register logic 0. And now, after doing that, it means we can read or write to registers in bank 0. When you are in bank 0, you can access registers in bank 0. You want to access registers in bank 1, you must first switch to bank 1 if you are in bank 0. And then if you are in bank 1, to access registers in bank 0, you must first switch to bank 0. Now we switch between the banks by setting or clearing bit 5 of the status register. Now this is our status register. It has 8 bits like all other registers in this microcontroller. And then bit 5 of the status register, the name of that bit is also RP0. RP0 is the name given to the bit 5 of the status register. Right. And as an example, switching to bank 1, we say bit set file status register, comma 5. We set bit 5 of the status register, and then this becomes what is in your status register. All of the other pins, they remain unchanged, but bit 5 becomes 1, and then this means we are in bank 1. We can access registers in bank 1, meaning we can access the trace A and trace B registers. We can configure our pins when we're in bank 1 by setting bit 5 of the status register. Right. To go to bank 0, we need to clear bit 5 of the status register. So as an example, switching to bank 0 there, we say bit clear file. The file is status register. The bit is bit 5. Be aware that this time around, I'm using RP0 instead of 5. These are the same. You can say comma 5 or comma RP0 because I said RP0 is the name for bit 5 of the status register. So whether you say comma 5 or you say comma RP0, it is the same thing. We are accessing and switching the same bit 5 of the status register. In this case, say bit clear file, status register comma RP0, bit 5 of the status register becomes 0. This means we are in bank 0, and now that we are in bank 0, we can access registers in bank 0 according to your memory organization. We're looking at registers in bank 0. We can access special function registers in bank 0 and also the general purpose registers. Right. Now, reading and writing to the input output pins. How do we read or write to the pins, to the actual pins of your microcontroller? Now, the port registers are used to read or write to the pins. The trace registers are used to configure the pins as either inputs or output pins. Bit 5 of the status register is used to switch between the banks. And now the port registers are used to read or write to the pins. Right. When an I/O pin is configured as an input, you can read the state of the pin by accessing the corresponding port register. Right. When an I/O pin is configured as an output, you can switch it on or off through the corresponding port register. And now remember, to access the port register, you must be in bank 0. Right. Now, as an example, this is how we will read port A3. If port A3 is configured as an input, we'll use an instruction bit test file skip if set port A, bit 3. So to access port A3, pin A3, we use port A bit 3. We can read the state of bit 3 of port A, meaning we are reading the state of pin A3 of your microcontroller. Now, switch off pin B4 of your microcontroller. We'll say bit clear file, port B, 4. We are switching off that bit 4, pin B4 of your microcontroller. Now, to switch on pin A1 of your microcontroller, bit set file, port A, 1, we are switching on that A1 pin of your PIC microcontroller. Right. Now, for all of these instructions, because you are accessing the port register, port A and port B, regardless of which port is it, both port A and port B, they are in bank 0. So these instructions should be executed while you are in bank 0. Right. Now, to be able to successfully write to an I/O pin, remember, we write to a pin, we switch it on or off. We write to it when it is an output. So to successfully write to a pin, that pin should be configured as an output. Right. If a pin is configured as an input and you write to it, that write is not going to be successful because the state of that pin is determined by the state of the input if it's an input. But now, if that pin is configured as an output, you can successfully write logic 0 or logic 1 to it because you are allowed to write to it since it's an output. Right. To read the state of the I/O pin, the pin should be configured as an input. For instance, if you want to read the state of the sensor, the pin on which the sensor is connected to, that pin should be configured as an input. Right. You cannot configure that pin as an output and then you connect a sensor to it and then you want to read the state of that sensor. It's not going to work. The pin has to be an output, an input, and then you connect that sensor to that input pin and then you can read the state of the sensor by reading that input pin. Right. Now, let's look at a sample example of a PIC program or a PIC instruction or an example problem. Let's say you want to switch off all port A pins and you want to switch on all port B pins. So you want to write 0 on all port A pins and you want to write 1s on all port B pins. The fact that we want to write to these pins, it means those pins should be configured as outputs. We write to outputs and then we read inputs, right? So the fact that we want to write zeros to port A pins must be outputs. And then the fact that we want to write 1s to port B pins, those port B pins must be outputs, right? Now, all pins must be configured as outputs through the trace registers. And then we need to write 00 to trace A, and then we need to write 00 to trace B in hexadecimal. Remember the trace register, when a bit is cleared, the corresponding pin is an output. So we want to clear all the trace bits so that all port pins are outputs. So on trace A, when we clear all trace A bits, all port A pins are outputs. When we clear or when we make all trace B pins zeros, all port B pins are outputs, right? Now, to access the trace register, we must switch to bank 1 because the trace registers are in bank 1. Before we can write zeros to trace A and trace B, we must first switch to bank 1 and then write 0 to trace A and then write 0 to trace B. Now, after configuring the pins as outputs, we now want to access the port registers so that we can write zeros on port A and then we write 1s to port B. But now, remember, we went to bank 1 so that we can access and write zeros to trace A and B. We now have to switch back to bank 0 so that we can access port registers. So we can access port A and port B. And then once we're in bank 0, we can write 0 to port A and then write FF to port B. Right. That's basically what we need to do. So the solution to that is, first we need to go to bank 1. So what we do is we say bit set file status comma 5. Remember we said setting bit 5 of the status register takes us to bank 1. Meaning whatever we do under this instruction, just underneath this instruction, whatever we do it while we're in bank 1. Because we have switched to bank 1 by setting bit 5 of the status register. We are now in bank 1. We can access the trace register. 2 ways we can write zeros to the trace register. We move 0 into W. W is our working register. So the instruction says move a literal value into our working register, which is W. So move literal to W. The literal value that we want to move to W is hexadecimal 00, meaning W has now in it 00. Now move the contents of W. Move W to 5. What is the 5? Trace A. The contents of W, now move them to trace A. Initially we moved 00 into W, meaning W has 00, and now we are moving that 00 to trace A, clearing all the bits of trace A, making all port A pins outputs, right? Now the easiest and simplest way of clearing a register instead of moving a 0 into that register is by using the clear instruction. Clear file trace B. I could have said clear file trace A, but I wanted to show you 2 ways you can do that. It's either you move 0 into W and then you move W to that register, or you can directly clear that register and then in this case you say clear file trace B, making all trace B bits zeros and then making all port B pins outputs. All of this we are doing it while we are in bank 1 because we set bit 5. We have managed to make port A pins outputs and port B pins outputs by moving zeros in the trace registers. Now we want to access port registers. To access port registers, we must go into bank 0. So what we do is we bit clear file status comma 5. We clear bit 5 of the status register. Clearing bit 5 of the status register takes us into bank 0. And now in bank 0, we want to write 0 on port A and we want to write FF on port B. We want to switch off all port A pins. We want to switch on all port B pins. So how do we do that? We can do that easily by clearing port A register or by moving 0 into port A. Either way will work. And now we move a value FF into W, which is all ones, and then we move W into port B, switching on all port B pins, right? So we move FF into W, and then we move W into port B, meaning we move this FF into port B, switching on all port B pins. Although there's a shortcut for moving 0 into a register, there's no shortcut for moving FF into a register. You have to move that into W and then move W into that particular register you want to move it in. So this is the simplest PIC assembly program that you guys will come across. And in this case, we were asking you to switch off all port A pins and to switch on all port B pins, meaning that you have to configure all these pins as outputs before you can switch them off. On default, all your microcontroller pins are inputs on default, meaning you have to configure them. If maybe the program required that your pins are inputs, since they are on default, they're inputs, you don't really need to configure them as inputs or reconfigure them as inputs, since on default they're inputs. But it is important that you configure your pins so that when you go and execute your instruction, you know that you have configured your pins in the right configuration before you can read or write to them. Right. Now, on this previous example, we said switch off all port A pins and switch on all port B pins, meaning write zeros to port A, write ones to port B. This is a statement. From this statement, you should be able to identify how you should configure and the program for configuring your inputs and how you will access and write to those pins. Now, here we are actually looking at how do you interpret a problem statement. Let's say you are given a statement. The statement doesn't tell you directly how to configure your pins, but you should identify from the statement how your pins should be configured. If the statement says you are expected to read port A0 to A4 and then write the value to port B0 to B4, meaning you read port A0 to A4. They're not telling you that those particular pins are inputs, but they're telling you that you are expected to read those pins. The pin that you read, it means that pin must be an input. The pin that you write to, it means that pin must be an output. So you need to be able to interpret from the problem statement how your pins should be configured if you're not directly told what should be input and what should be output. Other specifications, like maybe using timers and all of that, they will tell you how to set up your microcontroller, how to initialize your inputs, outputs, how to set up other peripherals like your microcontrollers and so on, which we are going to take a look at in the later stage. Now, the problem statement should also be able to tell you what is the beginning point, what is the next point, and what is the end point. Right. Now, in the previous example, we said you switch off all port A pins and switch on all port B pins. Initially, you will set up your pins as outputs, and then you go directly to switch off port A pins, and then the next step you switch on all port B pins. And then from there, there's nothing else to do according to the statement. It doesn't tell you what to do next. In this case, or in any other case, when you read the statement, it should tell you where to start. What is the initial point? What is the logic to achieve the next step? Or what is the next step? And then what is the final stage. And then once you have reached the final stage, whether you repeat the process or there's nothing else to do after reaching the final stage, the problem statement will give you those steps, right? So you need to be able to interpret your problem statement, find the keywords which will tell you which pins should be inputs, which ones should be outputs, how to configure or initialize your microcontroller, and then where to start, what is the next step, and then how to reach your final goal. What is your final goal? Problem statement should be able to lead you through all of these processes. Now, problem statement to flowchart. When you write a program, the first thing is, mostly you get a problem statement. You have to transfer your problem statement into a flowchart, and then from a flowchart, it's only then you can start writing a program, right? The process of writing a program, you take your problem statement, you convert it into a flowchart. Flowchart is the step-by-step process which will tell you how to approach the program writing process, step by step. Meaning at the beginning, what to do at the beginning? At power on, we should go and initialize. At initialize, that's where you set up your input-output pins. You configure your input-output pins, and you configure other peripherals which may be necessary depending on your problem statement, right? Now, after initializing, you then go into the main program. Now, the main program will depend on what the problem statement was. And then the main program can be broken down into smaller blocks, smaller steps, so that the main function can be achieved. This main function can be broken down into smaller steps, but those smaller steps, they will be guided by the problem statement itself. What is the initial state? What is the logic for the next state? And then what is the final state? And whether you keep on repeating the process all over again. Now, initialization. Why do we initialize our microcontroller, and how do we initialize our microcontroller? Now, we initialize our microcontroller because we need to inform it where we want our input and where we want our outputs, right? Depending on the problem statement or on the circuit we've constructed, where we want our inputs, where we want our outputs, and also to inform it or to set up other special function registers if we are using other modules or other peripherals in the microcontroller. We do that in the initialization process. We set up our inputs and outputs, and we set up other special function registers so that we configure our microcontroller depending on what the problem statement required. Now, to initialize, we need to access the special function registers. For example, setting input and output pins, we need to access the trace registers, which is our special function registers. So we initialize our microcontroller by writing to special function registers so that we can configure our pins and the microcontroller depending on the circuit and the requirements of the problem statement. And now, to access special function registers, remember we have two banks, bank 0 and bank 1. We must switch between the banks, ensure that we are in the correct bank so that we can access the correct register. If we want to access the trace register, we must switch to bank 1. If we want to access the port register, we must switch to bank 0, and so on. Right. And then bit 5 of the status register is the one that we use to switch between the banks. When that bit is set, it means we switched to bank 1. When that bit is cleared, it means we switched to bank 0. Right. Now, let's look at creating a sample MPLab program. Let's look at creating a sample project. And then in this project, we are going to solve the very same problem. And then this program, which we did and which I explained here, is actually an unstructured program. It does exactly what we are looking for, but I've omitted some overhead things which we are going to look at when we create a project. So I'm using MPLab 10 IDE version 5, Maybe by the time you look at this video, there will be a newer version of MPLab. To create a project, we say File, New Project, and then Microchip Embedded, Standalone Project. Next. Looks like my computer is thinking. And then you select the processor or the IC which you want to write the program for. I will type in here PIC16F84A, since it's the one we are using. Select that PIC. Next. Okay, the PIC, the hardware, the programming tool which I'll be using is the PIC3. So I'll select the PIC3 as a programming tool I'll be using there. Click next. I'll be using assembly language. So I'm gonna not a high-tech PIC language. I'll be using assembly language. So I'll select MPASM tool and then give your project a name. I'll say tutorial 1, and then where do I want this program to be saved? I'll browse. Let me browse to my memory device. Create a folder there and then call it tutorial 1. And then okay, it says new folder there. Okay, it's fine. It didn't rename that folder. It is still new folder. It's fine. And then just click finish. Now you have your project file here created. We need to create or to add to the project file what we call the source file. The source file is where you will be writing your program. So right click, new PIC sample ASM, give it a name. I can give it the same name as the project name, tutorial. The location, it is still the same location. Click finish, and then the file will be created with the file name .asm. Right, the file name .asm. Now to make things easy, I'm going to get rid of this already arranged structured program so that we can create our own program. Now this software here, it's MPLab 10 IDE. It's your compiler, right? It's your compiler software. And now this one is the source file. Now this MPLab can write programs for almost all PIC microcontrollers. You can write programs for all the PIC microcontrollers using the very same compiler. So when we write a program, we need to inform this compiler for which PIC microcontroller are we writing this program for. So the instruction for that, these are the overheads I said we skipped. We ignored when we implemented this solution. We ignored those overhead instructions which are supposed to be on your file, on your program file. Hence I said this is an unstructured program. Now let's look at what is needed for us to build the simplest PIC assembly program. You need to tell the compiler which PIC microcontroller you are writing a program for, and then you do that by using the list instruction. List P equals to 16F84A. That's how you inform your microcontroller, your compiler, that you are writing a program for this particular microcontroller. List P equals to 16F84A. Now, this next instruction is also very important. I will explain the purpose of this instruction later on. Hashtag include P16F84A PIC16F84A dot inc dot include dot inc. This instruction basically says make use of the file PIC16F84A dot inc. We're going to look at what does this file contain in it, but it just says in this program make use of the file, including this program, the file PIC16F84A dot inc. Now, one other most important thing when writing a program is there's always at the beginning. The program doesn't just run randomly from any location. It has to start running from somewhere. And now for a PIC microcontroller, that is our reset vector. We need to start running, or the program will always start to run from what we call the reset vector. Whether it's at power on, or whether you reset the microcontroller using mclear, or whether it is watchdog timer reset, any form of reset, or even at power on reset, the microcontroller will start executing instructions at the reset vector. And then for the PIC16F84A, the reset vector is program memory location 0. Right. So we say origin location 00. OX in front here. 0x in front means hexadecimal. I can just say instead hexadecimal value 0. It is still the same thing, but most of the time I use 0x to denote a hexadecimal value. So origin 00, this is at the beginning. We want to go somewhere. Go to initialize. Right. Now, a go to is our instruction. Origin 00 says this is at the beginning. This is the reset vector. So a semicolon means whatever that comes after semicolon is a comment. So let me try and maximize the window here. How do I do that? Okay, it looks like I can't do that. I don't know how to do it. It's refusing to work the way I've always done it before. But I'm assuming you can see there. So whatever that comes after the semicolon, it's actually a comment. You can write anything to state what is happening or what is that line of code doing. So basically here, this is our reset vector. This is where the program will always start executing after any reset. The program will start execution from 00, from program memory address 00. And now, what is it that we want? We want the PIC to jump to the location initialize at startup. At any reset, or after any reset, we want it to jump to initialize. So we say go to initialize. Initialize is what we call a label. So we can say go to start there, you must have start. We can say go to whatever you state there, you must have it somewhere so that the PIC will know where to jump to, where that initialize is. So when we write your PIC program, let me also do this. I'll add these things as we write the program. So here at the margin, I leave spaces at the margin because the margin is for labels. The margin, I'm leaving the margin for labels like initialize and stuff. And now the next part of your assembly program structure will be the instruction, the assembly instruction, and then the next part, let me do that, they call it the operand. where the instruction is being imposed, or whatever the case may be, right? Now we say go to initialize, and now initialize must be stated somewhere as our label. So we go to label initialize. At initialize, remember we are still implementing this program. So at initialize, that's where we want to set up our input and output pins. That's where we want to make all of these pins output. So at initialize, this is the program that comes in, exactly this program. So what's going to happen is at initialize, we're going to say bit set file status, comma 5, or we can say comma RP0. I said RP0 is the name for bit 5 of the status register. Bit set 5 status comma RP0, and then move literal value into W. The value is hexadecimal value 00. Move W to file. The file is trace A, and then we say clear file trace B. Remember I said these are the two ways of moving 0 into a register. Either you directly clear the register, or you move 0 into that register by firstly moving 0 into the working register, which is W, and then moving W into that particular register. Right, now we want to go back to bank 0 bit clear file status comma RP0. So here basically by setting RP0, we actually switch to bank 1. We move 0 into W. Okay, on this instruction, our W register has a value in it 0. And now when we move that 0 into trace A, trace A becomes 0 itself, which means that port A pins are outputs. All port A pins are outputs. Here, by clearing trace B, it means we make trace B still same as port A 0, which means all port B pins are outputs. Now here, what do? We switch back to bank 0. Now we are in bank 0. What is it that we want to do in bank 0? According to the program, we want to, or according to the statement here, we want to switch off all port A pins and switch on all port B pins. So we clear port A pins and we write FF to port B pins. So we'll do here, move literal value into W. Okay, we can use the shortcut by saying clear file trace A. We're already switching off all port A pins. And then we can say here, move literal to W. The value that we want to move into W is FF. Now it means here now our W register has the value in it FF. Right, now we move that value, move whatever is into W, move into the file. The file is port B. Right, this instruction tells us now our port B has the value in it FF, meaning all port B pins are now 1 logic high, they are now high. Right, we have accomplished that task. What we can do what we call an endless loop. Loop, go to loop. So basically here, the PIC will be stuck in this loop. It will execute go to loop. Where is loop? Loop, it is right here. So it will be stuck in this loop after configuring your inputs and outputs and writing 0 to port A, writing FF to port B. It will be stuck in this loop because there's nothing else to do, right? And then to conclude your program, there should always be the end instruction. This end instruction is never ever going to be executed by the PIC, but is an instruction that tells the compiler that this is the end of your program. It's an instruction that tells your compiler that this is the end of your program, right? Now we can build and see if this program builds successfully. I'm not expecting any troubles here. So it does. This is basically a basic assembly program where we have switched off all port A pins and switched on all port B pins. Now let's use a simulator program. PIC simulator program. It's actually OceanSoft PIC simulator program. This program has a trial version of 30 days. You can download the PIC simulator IDE program and use it, but it has a trial version of 30 days, right? Now you need to show your microcontroller. First we need to select the correct microcontroller. So by double clicking here, you can select which microcontroller. So we are using the PIC16F84A. So I select that microcontroller and then tools, microcontroller view. It will pop up the hardware configuration of your microcontroller. This is your microcontroller. These are the pin out: A0, A1, A2, A3, A4, B0 up to B7. VSS and VDD, they are not part of your IOs. You cannot control them via your program, so they are excluded from accessibility here. So these pins, like I said, initially they are configured as inputs, but if we load our program, say file load, I'm going to browse to my memory device, browse to that new folder, the project folder. In the dist production, access the tutorial hex file. The hex file is what is actually programmed. Although we are writing our program on .asm file, when we program our microcontroller, we actually use the hex file. So I'm going to import my hex file and I'm going to start. I can choose the rate at which the instructions are executed. Let's leave it at fast. Start executing instructions. You see what happens? Your pins are all outputs. The buttons have disappeared to show that the pins are now outputs. And now all of port A pins, A0 up to A4, they are all off. B0 up to B7, they are all on. Right? How did that happen? Let's look at it step by step. I'm going to change the program rate to step by step and say start execution. Now, initially, like I said, your microcontroller, the pins are inputs, all of them on default. Now, the first instruction we'll have is go to initialize. That's our instruction. Go to there. And then our next instruction is bit set file status RP0. Right? This makes us or helps us switch to bank 1. Now, after we switch to bank 1, we move 0 into W. Our working register is W. When we move 0 to it, the value into W is 0, 0. Right? And then we are going to move that to trace A. Our pins on default are inputs because trace A on default, all the usable pins, trace A0, A1, A2 up to A4, they are all set on default. And trace B, all the pins are also set on default. Red means they are set. White means they are cleared. Gray color means they are unused. Right? So because trace A bits on default, they are set. Port A pins on default, they are inputs. Trace A bits on default, they are set. Port A pins on default, they are inputs. We are about to move 0 into trace A. W has 0. We're going to move that W into trace A. So what happens? When we move W to trace A becomes zeros. And then what happens? The buttons which indicates that a pin is an input, those buttons disappear to show now that pin is now an output. We have now made only trace A outputs because our next instruction, trace B, is the one that's going to make port B pins output. When we execute, meaning when this instruction moves into this side, when it is executed, when we execute this instruction, trace B becomes zeros. The buttons on port B pins disappear. All of these pins are now outputs, right? Our next instruction, we are switching back to bank 0. Be clear file status RP0. When we execute that instruction, it's going to come to the side, and now we clear port A. We switch off all port A pins. They are already off, so even if we switch off, they're going to remain off. So we clear port A, it remains off. Our next instruction, we are going to move FF into W. Move a literal value FF into W. Currently W has 0, 0. When we execute this instruction, when it comes on this side, W now has FF. Hence all those blocks are red. W now has FF. Now we want to take this FF in W. We want to move it into port B. Now, write into port B means we are going to write these pins. We are going to write FF to these pins by writing to port B. So when we write FF to port B, all port B pins are high, right? All port B pins are high, and then port B pins has FF. Even the port B register has FF on it there, right? Now the next thing is endless loop. Main, go to main, endless loop. That's the end of your program, right? You can use the PIC simulator IDE to simulate and see if your program is going to run accordingly, and if not, see what might be the possible cause of your problem, right? So basically, this is the simplest assembly program you can do. Let's assume that you had LEDs connected on port B and on port A. The ones on port B you want to switch off. The ones on port B you want to switch on. That's how you would have done it. Or you want to do it the other way around. You want to switch off all port B. I will say here, clear file, trace B, move FF into trace, into port A actually. Clear file, port B. This must be port B. I'll explain why it worked even if you did trace there. Clear file, port B, and then move FF into port A. Clear file, port B, move FF into port A. Let's stop the execution, reload the program, and then start execution. This time around, FF will be written to port A and 0 will be written to port B. So let's start. And then we say now, go to bank 1 bit set file, move 0 into trace A, make these outputs, clear file, trace B, make those outputs, go to bank 0, clear bit 5 of the status register, clear trace B, make trace B, make clear port B actually, make port B pins off, and now move FF into W, move that to port A. When you move that to port A pins are the ones that are high now. Although we have A0 to A4, we said move FF to port A. A5, A6, A7, they are not used. So it doesn't matter whether you move ones to them or you move zeros to them, they are not going to play any role because you don't have pins associated to A5, A6, and A7. So only A0 up to A4 will switch on, right? Now, you must have been aware that I had trace here, a trace register here, trace A, and the program managed to work well, even though the file here was a trace instead of a port. Why did that happen? We are in bank 0. We switched to bank 0. Meaning whatever we are doing after switching to bank 0, whatever we are doing underneath, we do it while we are in bank 0. Right. Now, in bank 0, can we access the trace register in bank 0? No. Let's look at this. Trace register is in bank 1. When we are in bank 0, we access the port register. Even though I said move to trace A, but the fact that I'm in bank 0, I'm actually accessing the port A instead of the trace A. So when I say whatever, let's say I'm in bank 0 and then I say write to trace register, I'm not going to successfully write to the trace register, and as a result I will be actually writing to the port register, but because I'm in the wrong bank. If I want to write to the trace register, I must first be in bank 1, then I can access the trace register. If I want to access the port register, I must be in bank 0, then I can access the port register. If I try to access the trace register while in the wrong bank, in bank 0, I'm actually going to access the port, the corresponding port register. If I'm in bank 1 and I want to access the port register, I'm actually going to access the corresponding trace register because I'm in the bank 1, I'm not in bank 0. You must be in the correct bank to access the correct register, else you will access the corresponding address. Right. If you want to access the trace while you're in bank 0, you will access the port. If you want to access the port while you're in bank 1, you will access the trace. And then that will create, or that will cause a malfunction in your program because the trace register, you are setting input output pins. You might be modifying your input output setup, yet you wanted to switch on and off the pins, but you are setting them as inputs and outputs because you are in the wrong bank, you are accessing the wrong register. Right. So that's why it is important to switch between the banks before you can access a particular register you want to access. Right. So this is the simplest PIC assembly program language that we can do with you guys. And now, to add to this, there are other examples we can look into. We have already done this first one where we want to write 0 on port A, and then we want to write FF on port B. That's basically what we just did. Let's just do the second one. Very important here. You are expected to read port A and write the value on port B. They didn't tell you where the inputs are, where the outputs are. They just tell you read port A, and then the value that you read from port A, write it to port B. Right. And then maybe this you can do it indefinitely. You can keep on reading and reading port A, or you can do it once. You can read port A once and then write to port B, and then after reading and writing, then you go into an endless loop. Or you can repeat the reading and the writing process. Let's do this second one. We're going to do both ways of reading once and writing once, and then also repeating the reading and the writing process. Now, to start with, it says read port A, meaning port A must be inputs. Port A pins must be inputs. A0 up to A4 must be inputs. And then it says write to port B. Port B0 up to B7 can be inputs, but obviously only B0 to B4 will be usable because we have the corresponding A0 to A4 pins on the port A pin. Right. We don't have A5, A6, A7, meaning B5, B6, B7 will be redundant, sort of to say. Now, but we are going to set the whole of port A as inputs, the whole of port B as outputs. Let's do that. How do we do that? We go back to our program. I'm not going to modify this program. I want all of port A pins to be inputs, and now I want A0, A1, A2, A3, and A4. A5, A6, A7 are zeros, right? Let me do it simply by saying the binary value A7 is 0, A6 is 0, A5 is 0, A4 is 1, A3 is 1, A2 is 1, A1 is 1, A0 is 1. So in total it's 8 bits. 1, 2, 3, 4, 5, 6, 7, 8. Right. This is how you will denote a binary value on this compiler program. B dash the value dash. Right. Now, in hexadecimal, this value will be 1F. Move that 1F into W, move that to trace A. You are making all port A pins inputs. All port A pins are inputs. Now, to make port B pins outputs, we leave it as it is. Clear trace B. All port B pins are outputs. Now, the question says we are supposed to read port A. Now, I'm going to introduce more instructions here. These instructions, I said you can get them or you can find them on the PIC datasheet. Just download the PIC16F84A datasheet and then you can familiarize yourself with these instructions. Right. The instruction which we are going to use here, we want to read. And this time around, we are not reading just one bit of port A. We want to read the whole 8 bits of port A register. So we use a byte-oriented instruction. Move file. What is the file? The file that we want to read is port A. We move it into W. We read the state of port A pins and we temporarily save them into the W register. Right? And then what do we do? Now, W has the state of port A pins. We just take that into port B. We just erase this part. And then we say just move file, port A into W, move W file, move W to file. Meaning, now that W has the state of port A, move that into port B. Now, port B is equals to whatever that is in port A. And then after reading port A and writing it to port B, we go into an endless loop. Right, we go into an endless loop. Let's build this program and then simulate it. So let's stop and then reload the hex file. Start. Go to initialize is our first instruction. And then bit set file. RP0 of the status register. We go into bank 1. We move 1F into W. Then W is going to be 1F. You see, W now has 1F in it. We are going to move that into trace A. But trace A already has 1F. So it's going to remain 1F. So we move that to trace A remains 1F. The next instruction, we're going to clear trace B, which currently has FF in it, because on default, the pins are inputs, meaning all the trace bits are set. We need to clear them to make all the pins outputs. So we clear trace B. Trace B becomes 0, 0. All the bits are zeros and the pin on port B are now outputs. Now, we go to bank 0 now by clearing bit 5 of the status register. And then the next thing is we want to read the state of port A. Let's say A0 is high and A2 is high. I just click on those buttons there to make them on, or can click again to make it off. Click on it to make it on. A0 on and A2 on. And that's what we are about to read. And when we read port A with A0 and A2 on, W will have the state of port A. So we say read port A. W has 5 in it. Why? Because when bit 2 and bit 0 are set, in a binary value, bit 2 and bit 0 are set, the rest are cleared. That value is 5. Bit 0 is set, bit 1 is cleared, bit 2 is set. And then the rest of the other bits are cleared. That value is 5. Meaning we read port A and then the value 5 was moved into the W register. And now that 5, that value which we read from port A, is the very same value we are going to write to port B, meaning B0 and B2 will be set. So we say move W to file port B, B0 and B2 are set, the rest of the bits are still cleared, right? And then the next thing you go into an endless loop, right? Meaning we perform the read and write once, and then we go to an endless loop. The problem with going to an endless loop is if I change the state of the inputs here, even though the program is running, the state of the output won't change because we read and written once. We are not repeating the process, meaning we are not going to update port B with the changing state of port A. So to be able to update port B with the changing state of port A, we need to repeat the read and the write process. So we can say go to loop still, but our loop is not here. Our loop is where we start reading again. So if we put our loop here, so if we say go to loop, the program actually jumps where? It jumps here where it reads port A, is going to go to the next instruction, write to port B, and then the next instruction go to loop, jumps back there, read port A, write to port B. It's going to do that indefinitely. So whenever the state of port A changes, the state of port B will be updated. We build that and then reload our hex file. I'm going to run this a bit faster now because you already know. Now if I change this, see, when I change that, when I change port A, port B also changes. When I change the state of port A, port B also changes. Right. This is actually where our introduction to PIC microcontroller assembly language video ends. Please add more to this program. Try and do those other sample examples where you read port A, you invert the value, and then you write the results to port B. Maybe meaning you complement. You read port A, you complement the value, you write the value or the results on port B. The next thing is implement a 2-input AND gate. You implement a 3-input AND gate. You can decide where you want your 2 inputs and where you want your output. Now implement AND gate and OR gate in one program. In one PIC program, implement an AND gate and OR gate. So add more things to that program and then see how far you can go. I'll see you guys on the next video. Enjoy.